Your hosts today are Peter Stevens, well known as and from Agile and Scrum, Accelerator Problem Solver Listener, Ralph, a Lean and Kata enthusiast, management coach, and a researcher diving deeper into things and learning about the future, what's next. Myself, Markus Ganter, I have an R&D background and focus on lean management, the development side and the manufacturing side coming together as one, trying to create product process platforms and therefore customer value and internal value. We have prepared 3 examples for what the Tesla challenge is about. And we will start with Peter. And Peter, with that, I give the stick to you.
Okay, well, thank you so much. So I'd like to repeat Markus's welcome to everyone. My name is Peter B. Stevens. When I look at the work that I do with my clients these days, most of them are facing what I've come to call, kind of a SpaceX problem. Now, we see SpaceX particularly in the space industry, but we also see other industries like the automobile industry, might call it a Tesla problem, or they might even call it a China problem. And, the problem boils down to, it seems like the competition is faster, more innovative, and cheaper, and getting cheaper, and the challenge is, how can we keep up? Yes, we develop our products, but it seems like it takes us forever. And it seems like we get halfway into it, and then we realize we need to develop something else before it's really finished. So, how can we be faster and more innovative? Now, I don't know, I guess because of my interest in space and, cutting edge technology in general, I've been following Tesla and SpaceX for, at least 7 or 8 years now. Certainly since the Falcon 9s first started landing. And I've really been fascinated by them, both for what they have accomplished, but also because much of what they've done has really been in the public view, and we've been able to appreciate how they do it. And so what I'd like to do is, share a little bit about that tonight, look about how they do it, and maybe share some ideas about how you could do it as well. Now, some of you might be thinking at this point, but isn't SpaceX the company that keeps blowing up rockets? And if they keep having so many explosions, how can we possibly take them seriously? Okay. Now, the short answer is yes, they do have a lot of explosions. Oddly enough, they're kind of proud of it, in a strange sort of way. And what I'd like to do is show you a brief excerpt from a video where they celebrated these explosions. So if you have any problems with the sound, give me a shout or a wave or something, but it should be working on the first try. And so here we are, SpaceX and explosions. That ended abruptly. I'm not quite sure what happened there. The conclusion, however, is that by 2016, they had managed to successfully land a booster, first return to launch site, that is, they landed on the ground, and then a couple months later, they landed the booster on a drone ship, or basically a barge that was floating out in the middle of the ocean. And since then, well, some interesting things have happened. So let's take a look at what's happened since then. Okay. SpaceX got their start in 2012. Their first successful Falcon 9 booster landings were towards the end of 2016. When we look at this graph, the blue lines here at the bottom, this is the rest of the US launch industry without SpaceX. This gray line is the USA with SpaceX. Now, the USA line is close enough to flat that we can just pretty much ignore the difference. And we see that all of the growth has been coming from SpaceX. The exception here, by the way, has been China, which has been also rapidly accelerating. This is why we say maybe we have a China problem as well. China landed their first booster, I believe it was last summer, so about 6 months ago. SpaceX's nearest competitor in the United States, Blue Origin, they launched their first orbital rocket 2 weeks ago, with the objective that eventually they'll be able to reuse the booster 25 times. Now, at the same time, SpaceX completed the first time that one of their rockets launched and landed 25 times on the ground. And since SpaceX first got landing the rockets working, first of all, they've had a phenomenal success rate, virtually 100%. The number of successful landings or successful landing attempts is only slightly below that. And they're up around 400 launch and landing attempts with, I don't know, they had a string of around 300 successful launches and landings before they had an incident again. So what I'd like to do is explore, first of all, what's special about SpaceX? How do they do things differently? What are the guiding principles that we might be able to apply in our work? And finally, what do I think you need to do, or what do I think will help you accelerate to keep up? So ultimately, it's about speed of development, and economics, that is operating costs. So what we're looking at here is a long-term view of launch costs, not per launch, but rather per kilogram of payload into orbit. Now, you look at it and you think it's a linear graph, then you look more closely at the scale on the left and you discover it's actually a logarithmic scale. Okay, so that basically each line, like from 1600 to 3200 to 6400, each line represents a factor of 2 increase in the cost of getting a kilogram of payload into orbit. And the other thing we notice is that since the mid-1960s, most of the rockets that have been developed are somewhere between, I'm going to guess around $8,000 and around $16,000 to $18,000 per kilo. A notable exception was the space shuttle, which was the first attempt at reusability, which proved to be a very expensive attempt at reusability. That didn't change much until SpaceX came along. Their first rocket was the Falcon 1, which was actually kind of at the upper end. It was a very small rocket. But then came the Falcon 9. And if we look at that, that's a factor of 2, a factor of 4, maybe a factor of 5 reduction in launch costs compared to where they were in the middle of that range. The Falcon Heavy lowered it even more. And the Starship has the goal of lowering that by another factor of 10. Okay, so what they've gotten here is a huge cost advantage. And notice the emphasis here is on operating costs, not on development costs. I don't care what the development costs are as long as they can afford it. The question is, do they have an operating advantage? Because that's what moves the needle. And so how do they do that? Well, here we see 3 generations of the flamey end of the rocket, the Raptor engine. It's really about technology, innovation, and the leadership of the company. Okay, and so we see here on the left, this is the first version of the Raptor. This is the one they were using up until quite recently. Right now, I believe most of the rockets are now using Raptor 2s. Raptor 3 is what they currently have in development. And, a traditional approach to building rockets probably would have stopped at the Raptor 1. And say, okay, we got it working. Let's fire the rocket. We're good. With SpaceX, they continued iterating on it. And among other things, if I remember correctly, from Raptor 1 to Raptor 2, they saved 1,000 kilograms per unit. And from Raptor 2 to Raptor 3, another 1,000 kilograms. So you multiply that by the 30-odd engines in the rocket, and you've discovered they've saved about 60,000 kilograms in gross weight, making that available for payload. Now, how do they do this? Well, first of all, the core realization is that the speed of innovation is really their only lasting competitive advantage. So that's why they don't worry too much about being photographed by the outside world, because they know that they're faster than anybody else. So how do they do it? Well, they've actually talked a lot about how they do it. You find it in their annual reports. You find it in YouTube videos prepared by the press. And at the heart of it is what they call the innovation algorithm. And it's a 5-step approach. Step 1 is make the requirements less dumb. Okay, so the idea is every list of requirements, well, is any list of requirements perfect? And the answer is almost by definition no. So there are some requirements that you can take out or reduce, simplify, make more intelligent. Then you start looking for ways to simplify, that is, eliminating parts or process steps. Okay, every part that you produce costs money. Every process step costs money and takes time. If you can eliminate either one of them, you're saving time and money. And in this case, that gives them more payload going to orbit. Then they optimize. Okay, so basically they're going to continue iterating on steps 1 and 2 until they believe that they've really gotten that as far as they can go. Now, related to this is the concept of acceleration. Let's get the results sooner. Okay, there's always something you can optimize in the process. Just today, Tesla announced that they had opened a tunnel from one side of the factory, which had to cross the interstate highway, onto the other side of the factory for the Cybertruck, which saved 60 seconds in the manufacturing process. And I was reading the comments about that today in Reddit, and they were saying, what difference does 60 seconds make? Well, 60 seconds is a minute shorter in an industry where companies can, measure themselves by how long it takes to produce a vehicle. And it doesn't seem a lot, but those 1 minutes, they add up. So this is the concept of acceleration. And only when they're convinced that they've optimized it where there's nothing left to optimize, this is when they start to automate. So when we go back to the Raptor 1, well, the first goal was to get it working and to get it working reliably. Raptor 2 was the result of many, many years of optimization. And then Raptor 3 is saying, it's actually the same design as Raptor 2, but all of those pipes that are hanging on the outside, well, they're now internal to the casing. And then a lot of this is 3D printed. And so this is designed to make it more efficient to manufacture. And that's the basis that they're going to start automating on. Okay, so how can you accelerate? Okay, and I really think the key here is the leadership in your organizations, which is both visionary and effective. So what do you have to do? Well, both SpaceX and Tesla are characterized by very long-term vision, well beyond, the profit goals of this quarter. And what they're doing today is there to support the long-term vision. Now, obviously, they have to execute. They have to be able to maintain focus on their long-term goals. At the same time, we get new information. Some things don't work the way we intended. So we need to be able to respond to change effectively. In the case of SpaceX, they realized the launch market was not going to pay for their ambitions to go to Mars. So they had to come up with a plan B. That plan B became Starlink. And Starlink has revolutionized the communication industry, which is in turn revolutionizing everything from disaster relief to military engagement. And so what you have is a very, very close collaboration between what's happening at the strategic level, what's happening at the tactical level, and what's happening at the operational level. And in fact, pretty much everybody at SpaceX or Tesla is expected to be in the factory, working at the factory. And then finally, as leaders, we are also creating the environment where all these other things can happen. So what that means is, what do we do as managers? Well, the most important skill is communication. And there's a lot of potential for improvement here. And each and every one of us is challenged to learn new tools and develop new skills. Now, one of those possible tool sets is extreme manufacturing. Extreme manufacturing emerged independently of SpaceX, but encapsulates many of the principles that SpaceX is applying. Now, I'm not going to go into all of them, but I do want to take a look at this concept of test-driven development. Okay, first you create a model, then you build it, then you validate it, then you repeat, you keep going until the model is the test. So let's look at the SpaceX test program for the upper stage known as Starship. Now, when SpaceX made the switch from carbon fiber to stainless steel, they had never worked with steel before. So after they had acquired some land, they decided to put the plant on that plot of land in what's now known as Starbase, Texas. And what was the first thing they did? Well, they sent their engineers down there with notebooks and cell phones, and they started buying steel and hiring steel workers. And they put up tents, and then they ordered bulldozers, and then they watched YouTube videos to learn how to operate the bulldozers. And as you see, almost really from the get-go, they were building stuff. And so in the left here, we have their first test tanks, where the goal was literally, can it hold water? Then can it hold cryogenic fluids? Then we start building something that looks like a rocket ship, sort of, or maybe a big water tank. And in fact, the early versions, the serial numbers 5 and 6, they were called flying water tanks. And they said, why is SpaceX building water tanks? And you see these things here that look like explosions? Well, they call that a rapid unscheduled disassembly. That means they tested it and it failed when it wasn't supposed to, but each one of those was a learning experience. And by the way, each one of these prototypes is about 1 month apart. So about a year later, they had gotten to the point where they were ready to do suborbital testing. Here they're testing the aerodynamics and can they make it do a cartwheel and land on its tail? They knew it could land on its tail because the first flying water tank landed on its tail, but getting the whole cartwheel, the whole aerodynamics going, proved to be challenging. And it took them up until, well, I think a total of 5 tries. Here you see the test firings. Here you see the various other tests. And finally, they had a successful landing. They actually had a successful landing followed by a RUD a few minutes later. 2 iterations later, they were able to land successfully. And so when we look at this a bit more formally, and this is now based on the booster side of it, you see that they've defined a series of tests. And with each attempt that they make, they run some tests, they get a bit further, okay? They keep going until they either fail or they pass and they move on to the next one, okay? And booster 12 was a successful catch. Booster 14, when I made this, had not yet flown. It was also a successful catch. Booster 13, I would describe the catch as a successful failure. It actually aborted and did not attempt to get caught on the tower because the parameters weren't there. So it landed, so to speak, in the ocean. Okay. Now, we see this happening much closer to home. Here we see Bosch iterating on the design of a park distance control for locomotives. So they already made park distance controls for cars, the things that go beep, 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 beep when you are, when you're backing up and getting too close to something. Locomotives have a similar problem in the train yards. Their first iteration was to take an existing park distance controller, attach it to a locomotive and see if it works and see if it brings value. The answer to both questions was yes. So in basically 1-week intervals, they got it down to the design that they wanted to have for the locomotives. And from initial idea to finished prototype took 5 weeks. So anyway, so that's kind of a look at how it could be done. Can you do this? I think Bosch brings the proof that it can be done, even in Europe. And so I hope that I've whetted your curiosity. We'll have some discussion at the end, but I'd like to invite you to reach out to us and start a conversation. For me, the focus is really this hardware, software, hybrid product development. Organizations who feel like there's a missing we in the company, where there's too much internal friction within the organization. Obviously, agile transformation is a topic, especially if it's not going the way you like. And I do a lot of advanced workshops on agility. And so with that, I would be very delighted to have a conversation with you. And I will pass the talking stick back to Markus.
I think I handed over now to Ralph. Ralph is with the second use case, and
yeah,
this is a car company, I guess.
Yes, it is. So, good evening from my side. I'm very pleased to share some insights about Tesla. And my name is Ralph Winkler. I'm a lean expert with a strong background in industrial engineering and industrialization. And I caught interest in Tesla pretty early as I actually tried to apply a Tesla in 2007. I already prepared a CV, but never sent it because I met my wife here in Germany and decided to stay here. So maybe a missed opportunity. I don't know. We'll see. So, the topic for today, I will discuss and show you why we think the automotive industry has a Tesla problem, or in other words, Tesla presents a significant challenge to traditional car manufacturers, and I want to share some of our insights. What to expect? So I want to share some. I want to address the elephant in the room. I want to share some of the results that we can see at Tesla, and then I want to do a brief look under the hood and show you some examples I prepared. Two examples, to illustrate the Tesla's unique approaches that leads to their tremendous results. First and foremost, as I'm a lean expert, very familiar with Toyota, and Toyota as the mother of all production systems, mentioned that they are really impressed when they have done a tear down of the Tesla Model Y, and stated that they saw a real piece of art under the skin, and also mentioned that they were not able to um, do the same right now. And therefore, I was really impressed, so that they mentioned, and I was really surprised that they mentioned they could not do this. Um, um, and they were really amazed about the innovative design that they could see there. And on the other hand, we can see the numbers, like the comparison here of the assembly times, assembly hours for Volkswagen ID.3. It's approximately 30 hours compared to a Tesla Model 3 that's around 10 hours. So Tesla is more than 3 times faster than Volkswagen. When we look at the profit margin per car, we can see that Tesla is still the benchmark, even if they have slightly dropped in the recent weeks and months. And what's also interesting, that the Chinese car companies are catching up pretty quickly, and the Chinese OEMs stating now that they do no longer benchmark German manufacturers, but take Tesla as their reference and benchmark to Tesla and try to copy and mimic what Tesla is doing. So that's pretty interesting. So let's have a look on the selected approaches. One thing Peter already mentioned is that we see that Tesla and SpaceX use really ambitious, meaningful long-term targets. So the mission statement, Tesla's mission statement here, is to accelerate the world's transition to sustainable energy, and only the midterm vision is to be the best car manufacturer in the world. So this is pretty meaningful, and maybe attracts the right kind of people to work there. But they also use some methodologies to derive more tangible midterm targets that are still very much out of the box. And there I see kind of a similarity to the True North, Toyota's True North thinking. So the two approaches that we can observe with Tesla is the so-called idiot index and the first principles that they use to derive more tangible out-of-the-box targets to align the whole organization. So what is the idiot index? It's the ratio of total production costs to raw material costs. This is a very simple approach to evaluate your production and processes, and leads to a very good and simple insight where you have to improve. So the guiding principle here is, if the ratio is very bad in a serious production, either the product design and or the process design is inadequate. So we use this already with some of our clients, and this is very good because it's so simple to figure out where to emphasize and where to do further improvements in a process. The second principle they use is the first principle thinking. This is deriving goals from fundamental truths instead of analogies, doing just a little bit more or a little bit less of what you have doing so far. So Tesla uses here often a breakdown in fundamental physics. For instance, when they when they set up a target for the acceleration of a car, they just use the physical equations to determine the target for how fast should a car accelerate. So the guiding principle here is what is physically feasible. Based on this ambitious long-term goals, sub-goals for product and process are derived at Tesla. And this is something, it's not completely new, but it's very interesting to see that they use it very good. The 10 principles of extreme manufacturing, I want to emphasize on object-oriented modular architecture a little bit. Tesla took an inspiration from Matchbox cars and questioned itself, why not build cars as efficiently as Matchbox cars? And they took this inspiration from the toy cars and figured out that there are just 4 essential modules that are assembled at the end, and tried to apply this on their car production. And by doing so and translating this into a production process, they developed a pretty unique technique for car production. And this new process is called the unboxed process. If we compare a traditional production process, like shown here on the left side, something we would call a boxed process, because all the value-adding steps are here in the line in one box. And the so-called unboxed process from Tesla is like they unpacked the production process based on the modules they have defined, and so created more like a fishbone-like production where they can produce the modules in parallel and therefore achieve some advantages with this approach. I will show you some of the advantages. The first advantage is the free access to the product and the shorter distances. On the left-hand side, you see a traditional interior assembly at Audi, where you can see that the operators have to get in and out into the body. And this is very stressful and not simple. And we can compare this with an unboxed assembly from Tesla. It's on the right-hand side. So one of the advantages is that the free access, the shorter ways, the smaller footprint, and also the possibility for automation is much higher in this approach. The second advantage is the parallelization of the innovation process. Due to the decoupling of the production process, they are able to keep their rate of innovation very high, as they can optimize each and every module in parallel without interfering the other modules and the whole production line, without line balancing at the end. And I show you some examples how they brought down cost, weight, and power for some of the modules during the life cycle. And the third advantage of this approach is, and it's maybe a precondition actually, that they use an analogy from the extreme programming, so that all modules are tested before the final assembly. This is inspired by software development. Tesla ensures that every component is tested early in the production. Each module undergoes rigorous testing before been integrated into the final vehicle. The so-called factory mode enables this, as all the modules have computer or controllers that autonomously test, calibrate, and do a fault detection. But Tesla doesn't stop here. They even use the idea of modularization to determine their organization. There's one saying in Tesla that the process is the product, and this has implications for the Tesla's organization. They also believe that all problems are a reflection of the problems in the organization. So they incrementally work on mimicking the product, process, and organizational structure as once. So they work in interdisciplinary teams with designers, engineers, manufacturing, and automation right from the start. This is an agile and fluid teamwork approach using some approaches from Scrum, but it is not Scrum what they are doing, but an agile work. So that was a brief insight from my side. There's much more details, much more to learn, much more to adapt. My key questions for you are, what are your insights? What did you find most interesting so far? And I'm really looking forward for the questions in our Q&A later on. And I pass the stick to Markus.
Thanks, Ralph. And I want to talk about a company that is not run by a billionaire and a startup expert and a very special personality, but a company that is working in the defense area, which is also quite regulated and quite complex in terms of customer requirements. This is the defense industry, and we're talking about Saab having exceptional results against fierce competition from North America. We're talking about the development of the Gripen version E. This is a 4.5 generation stealth jet fighter, so all the radar things, not detectable things, and it's multi-purpose like many jets today, air-to-air combat, air-to-ground, and reconnaissance missions. The requirements on usability, maintenance, upgradability are tremendous, and they really drive the life cycle costs for such a product, which is 30 plus years. Modularity is an obligation for a jet fighter. The functional elements need to be developed independently, but come together as a whole, and maintenance and upgrades are usual. And some of the systems, like electronic warfare weapon systems, may be country or region specific, means exchangeable. The requirements are hefty, and I just want to pick out a takeoff runway of 800 meters times 16 meters. That's actually a road, a 4-lane road. In combat, 15 minutes refueling, re-weaponing. Wow, how do you design that? And the ease of service and maintenance later in the product life cycle needs training for skills, tools, spare parts, and specific facilities to do that. The most advanced jet fighter today is Lockheed Martin's F-35. And the project costs are tremendous. The total cost means projects and purchasing cost and maintenance lifetime costs come up to 1,500 billion US dollars. And there are several institutions mocking about that, including financial ones. One unit costs 177 millions. So a comparable jet fighter is the Saab Gripen E. And why are there two jets there? Because for the price of one F-35, you can get two of the Gripen E. And there's a publication, Chains Aviation Weekly, very specialized on weapon systems. They were comparing the different projects, and Lockheed Martin's F-35 was kind of a technology project. So every supplier was trying to put as much novelty into the project and get as much of the budget. And actually they were exceeding budgets on a regular basis. Whereas Saab was focusing on a very different thing, which is the usability and the operational cost. Looking at the just technical performance, both jets are very close to each other. We don't need to get into detail. If you look at the project cost, Saab has managed it with 50 billion, and the F-35 was 28 times more. Incredible difference. The unit cost, as I said, 50%. But even more important, over the lifetime of the product, the flight hour cost is also only a fraction of what the F-35 would cost. If you're looking into detail, the US has a government accountability office, and they issued a report last year. What's the status of the F-35? And the major problem here is once you get a jet, well, then good luck with keeping it ready for flight. Skills, training, spare parts, technical equipment to have this fighter jet ready are just not there. So actually, the three major customers, US Air Force, Marines, and I think Navy, of course, they had to reduce the operating hours per year of the fleet they were buying just to be able to still afford this weapon system. Saab, in comparison, were focusing on even deployment in remote places. In a war, typically it's very easy to bring down an air force just by bombarding the runways. You don't even have to hit the jet fighters. They cannot start and land anymore. So they have a decentralized approach to warfare. And this is this is 3 jets, a very not high-skilled staff. You have weapon systems ready to be exchanged, refueling happening. They have 12-hour shifts. So they are signing a use case for decentralized deployment and are building the product and anything around for maintenance according to that. Again, we can identify here a couple of systems methods that we call extreme manufacturing. And here I want to focus on the modular architecture and that product and production and maintenance even become one. So how actually did they achieve it? They did a lot of testing right in the beginning. Once the requirements were clear, they iterated how systems can work together. And there's a certain point in a project where you have to freeze things and where the cost of change is really rising dramatically. They paid attention to that. Plan, do, check, act, that's the lean word for it. Design, prototype, test, review, inspect and adapt may sound familiar from the agile people. And that's also my personal journey. Looking at lean, starting maybe lean development, being documented in the 90s. And looking at what extreme manufacturing is, there are a lot of similarities, but Scrum could actually accelerate some of the lean principles dramatically. So how does this all happen? The product and the development and the future production, assembly, maintenance, upgrades are happening in a room. The different people from the different modules come together and they can physically understand and discuss iteratively how to approach different things. So this is something where it's not separated, design something in 3D models, and then later on they try to build it. It's coming together physically. The other thing is they break it, of course, down. So there's a scrum of Scrum happening for the engine, for the cockpit, and cockpit systems, electronic warfare typically changes at least every 10 years. So this needs to be modular, exchangeable by definition. But already in building the core structure, you can identify accessibility to things that need maintenance on a regular basis. And you can define interfaces and openings already, and hopefully physically in the first place, and not doing it in 3D models. They were working in sprint length of 3 weeks, and the Scrum meetings were happening every 30 minutes on actually 5 levels. And 2 times a week, there was the executive action team. So any impediments coming up could be resolved immediately, and the teams didn't need to wait to come to a decision, conclusion, and continue their work. So this was the third use case, defense industry, European-based, to give you an inspiration. And with that, I would like to open the discussion.